So lecture 72, Newton and the apple, universal gravitation. So this was Newton's big, the big breakthrough, okay? So for all of recorded history before Newton, people had been concerned with two different types of mechanics, right? What they would call terrestrial mechanics, that's the stuff that Galileo did with balls rolling down inclined planes, right?
Yeah.
And celestial mechanics, that's what astronomers did. They tracked the position of the planets moving throughout the sky, right? And under Aristotle's kind of paradigm, these two realms were separate, right? He even regarded the kind of matter that things in the heavens were made of were a different kind of matter than the stuff down here on Earth. Now, Newton was the first person to connect the two pieces, right? So the legend is that he was in his garden at his family farm, and holding an apple. He had an apple tree. I think the apple tree is still there, actually. Looking at the apple and thinking, could it be that the same force, right? We'll call it gravity because we know what it is, that affects this apple and makes it fall from the tree to the ground, is the same force which holds the moon up in the sky? Or holds the moon is a little strange statement, but he thought, well, maybe the moon is just falling like the apple is, okay?
All right.
And so if you were to do a computation on this, give me a second. I'm not going to derive this, but you can find this elsewhere, right? The acceleration near the surface of the Earth we call g, right? It's 10 meters per second, or 32 feet per second, right? And we'll call it a sub m, the acceleration the moon would feel, right? Because of, say, the gravity from the Earth, right? If we took the ratio of those two, right? You remember that from the last lecture, Newton showed that this force would obey a 1 over r squared law, right?
Yeah.
So we've got 1 over r squared for the Earth divided by 1 over r squared for the moon, right? What are these distances? Well, I'll get to that in a second. Let me just write down r Earth squared over r moon squared. So r Earth, what is that? That's the distance from the center of the Earth. Okay, this was stuff that Newton did in his Principia, right? He said that the gravity that you feel on Earth acts as if it was a point particle located at its center of mass. Okay.
All right.
So we would treat the center of the Earth as like the point where the gravitational force is directed towards. Okay. So our Earth is just the radius of the Earth. So if I'm standing here on the surface of the Earth, the distance to the center is the 1 over. That's the thing we use in our 1 over r squared law. Okay.
Okay.
And did I get that right? No, I got these exactly backwards. This should be the other way. It's r moon over r Earth. The squares of those. Okay.
Okay.
And then r moon. Well, that's the distance from the center of the Earth to, say, the center of the moon. Okay.
Okay.
So much larger distance, right? And it turns out this is approximately 3,600. Okay, that's the ratio. Now, they knew what the period of the moon was and stuff like that, so they had these estimates of how far away the moon was. Okay, again, I'm not going to go into that in this lecture, but you can show that. Okay?
All right.
Which means, right, remember, if we think about distance, right, it's 1/2 a t squared, right? So if we allow the time that something is going to fall to be 1 second, right, we can ask, well, how far would the apple fall in 1 second under this acceleration, right? So 1 squared is just 1, right? And so this is going to be, it's going to fall this far, right? 1/2 g, which is going to be, if we do it in meters per second, right? Then g is 10, roughly.
Yeah.
So that's, approximately 5 meters in 1 second that the apple will fall. How far does the moon fall in that time period, right? Well, if the ratio is this, right, then it's going to be, d moon, the distance the moon falls in that same 1 second is going to be on the order of 5 meters over 3,600, right, in 1 second. Okay?
Okay.
So he thought, well, maybe that's what's happening. So how does that make any kind of sense? Well, I'll show you. He actually had an illustration in his in the Principia. It had a little planet like this. It had a bit of a mountain on top of the planet, right? Atop which there was positioned a cannon. That's a terrible cannon. There we go. That's a little better. And it said, okay, well, if you fired that cannon, right, with just the weest bit of velocity to start, right, you can see what the trajectory of the cannonball is going to be. Right, it's going to do something like that. It's going to obey this. I guess I should put the t squared back in. this law from Galileo, right? It's going to follow a parabolic path, yes?
Yeah.
If we fire it with a little more oomph, right, it might do something like that. But notice that it's traveled, right? The travel time is a little bit longer. And the reason why is because the Earth is curving downwards, right? It's a little bit like throwing a ball off of a hill, right? If I throw the ball on a flat space, it's going to hit the ground sooner, right, than if I drop it, say, off of a ledge, right?
Yeah.
So as the cannonball is traveling and it's with its linear velocity, it's also being accelerated downwards towards the center of the Earth, right? And it's causing it to curve. Well, if you could shoot it fast enough, Newton hypothesized, then you would always miss the Earth. The Earth would always be curving underneath it, right? And the cannonball would just go around and around and around and around. And that, of course, is what we call today an orbit, you see?
Yeah.
So he said, well, that is what the moon is doing. That is how the moon is falling, right?
Yes.
Does that make sense?
Yeah.
Yeah? This was his big idea, that the same laws of physics which govern terrestrial bodies, things here on Earth, are the same. It's the same physics that governs the celestial bodies, in the sky, the planets and such. So that was a big breakthrough in thinking, and it changed the way people thought about the world from then on. So it's one of the major revolutions in thought in the history of the world. Okay?
Okay.
And that was, if there was any takeaway point to that, 1 over r squared, well, yes, that's nice. Physicists like it, but that was not the big thought. It's not the big thing that changed when Newton came along. Okay?
All right.
So there's one thing we've shown in the past lecture, right, that we get this 1 over r squared law for these orbits, right? And there's one little piece that we're missing that we need to put in. And so to do that, I'm going to show a very simple derivation of a 1 over r squared law. So we're going to make a big assumption. We're going to assume a circular orbit. So we'll put the sun here at the center of a circle of radius. It's typical of my circles, of radius r. Okay, and we're going to put the Earth out here in a circular orbit. So what that means is that we're assuming that the Earth is always a constant distance away from the sun. Of course, it's not. It's elliptical, the path, but if we pretend for a moment that it's circular, which it almost is, right? The ellipticity, or excuse me, the eccentricity of the Earth's orbit is not very great. It's easy to see why earlier astronomers assumed that it was circular, okay? So if we assume that, right, and we take into consideration Kepler's second law, right, the equal area and equal time law, right, that basically says, as we showed in a previous lecture, that the sum of the torques, right, about the sun, right, is 0. Which means that if there's any force that's acting between the sun and the Earth must be acting in the direction of the line that joins them, okay? So in this direction here, okay?
Okay.
This was equivalent to the statement that the angular momentum of the Earth-Sun system is conserved, okay?
All right.
So if that's the case, let's write down, call it equation 1. What is the period of this orbit, right? Well, the period is, of course, the circumference of this circular orbit, 2 pi r, over v, right? So if I take the velocity times the time that it takes to go once around this circle, that should be equal to the circumference. That's basically what that says, right? That's straightforward. And recall Kepler's third law, right? We'll call this equation 2, which says that t squared is equal to it's proportional to the radius cubed. If for a circular orbit, this would just be the radius of the circle. If it's an elliptical orbit we're talking about, this is the mean orbital distance. It's also the semi-major axis of the ellipse, okay? But we're going to assume that it's a circular orbit, so it's just the radius of this circle. So there's this relationship that t squared is proportional to r cubed. Okay, and this constant of proportionality, k, is just some constant. Okay, it cannot depend on the mass of the planet we're talking about, because remember, he observed that this holds true for all the planets. Okay? So independent of their mass, this is true. And so that'll turn out to be important. So what do we do with this? Well, we can plug 1 into 2. Right? What are we going to get? We're going to get 4 pi squared r squared over v squared equals k r cubed, right?
Yeah.
Let's solve. What do I want to solve for? Velocity, right? Yes, velocity. And we'll call this equation 3. If I solve for the velocity, I'll get v squared equals 4 pi squared over 4 pi squared over k r. Is that right? r cubed over r, yeah, that, or excuse me, r cubed here, k is over here. Yes, I think that's right. 4 pi squared over kr, okay?
Alright.
So that's just solving for v squared here in this term, yes?
Yeah.
That, you'll recall, is the velocity of the orbiting body, okay?
Yeah.
If v is 0, of course, we don't have an orbit, we just fall straight in, right? That's like the cannonball just falling out of the front of the cannon, right? From Newton's theorem 2, he said that the centripetal force was equal to mass of the Earth times v squared over r. So this is a kind of combination of Newton's second law and his theorem 2, right? The mass times acceleration. So he said that the centripetal acceleration is v squared over r, and that force is mass times acceleration. So this is what we'll call the centripetal force, mass of the Earth times v squared over r. And we'll call that equation 4, I guess? Yeah, 4. So if we plug 3 into 4, what do we get? We get Fc, the centripetal force, is equal to 4 pi squared over k times the mass of the Earth divided by, wait, there's a 4 pi squared, r squared, there it is, r squared. We now have our 1 over r squared law again, right, for this centripetal, for this circular orbit. But what about this constant k? Well, that's a bit tricky, but recall that Newton's third law, Newton's third law says that for the force between two objects, right, if we have two objects interacting, right, there are no external forces, then the force on one object, say object A, will be equal to minus the force on the other object, right?
Yeah.
So they're equal and oppositely directed along the lines that join them, but they're equal, right?
Yeah.
So, and then Newton's second law, right, would say that this is the mass of A times the acceleration of A would be equal to the mass of B times the acceleration of B. Both of them have the mass of the body in question in them, right?
Yeah.
So there's an equal and opposite force that the Earth, or the Sun, feels because of the Earth, right?
Yeah.
And that would, of course, have the mass of the Sun in it. So it must be the case that this K constant here, which we know already does not have the mass of the Earth in it. That's why the different planets, right, they all obey the same proportional law, right?
Yeah.
The proportionality constant has something to do with the Sun. And what it has to do with the Sun is the mass of the Sun is in there, okay? So we can say, and I'm just going to call it F now, right? This is Newton's gravitational law, is equal to big G, M1, well, let me write M Sun, M Earth, divided by r squared. So what is this big G? Well, 4 pi over k is equal to big G times mass of the Sun. Okay?
Yeah.
That looks like mass of sin. Let me write Sun. So I've kind of put it in with that, okay? And so now we just have this one constant that remains to be resolved. This is some proportionality constant, which does not depend on the mass of the Sun, right? Because we've taken that out. When we put this back in, right, we're going to have this mass of the Sun in the force law as well, okay?
All right.
So again, the reason why it's there is because of Newton's third law, okay?
All right.
F equals ma. So if we consider the equal and opposite force, right, that the Sun feels because of the Earth, it will have the mass of the Sun in it. So the only way that these two forces can be equal is if whatever force law we come up with must have both of those masses in them, okay?
All right.
We saw that we already had the mass of the Earth in it the way that we derived it, right?
Yeah.
So it must be that the mass of the Sun was coming into the constant k somehow. First, let me just write the universal gravitation formula down. Big G, and we'll write m1 times m2 over, call it r12 squared, okay? So that's the distance between body 1 and body 2, okay?
Yeah.
And this constant G, right, how do we determine that? Well, I think, when did they, I don't remember when they did. I want to say 1890, but that seems awfully late. Maybe 1790? That seems too early. I think it was sometime in the 1800s, scientists by the name of Cavendish constructed an apparatus. Try to draw it here. Put torque, some angle theta that it rotates, okay? And what they did is they would then suspend two larger masses. We'll call them M1, M1, okay? There's two of these. If you take a wire and you twist it, right, it's a little bit like a spring, right? The more you twist it, the larger the torque to untwist it is, okay? Just like if I press a string, the farther I press it in, the harder it pushes back to try to get back to equilibrium, right?
Yeah.
So he constructed an apparatus where he had two known masses that were large, M1, okay, and two small masses, M2. And he was able to make very careful measurements on when this thing kind of balanced out and determine what the gravitational constant was. And he got a number that was 6.67 times 10 to the minus 11, I think, Newton meters squared per kilogram squared. That seems right. Kilogram squared up here. Yes, I think that's right. Okay, so using this apparatus, this torsion system, he was able to determine what the gravitational constant was. And so now we have that. And so last thing I'll mention, right, is this little g that we've been talking about, right, that's 10 meters per second, or 32 feet per second, right, what does this have in it? Right, this has got big G in there. It's got the mass of the Earth and the radius of the Earth squared. Yeah, because we basically were taking F equals big G, mass of the Earth, over R, Earth squared, times the mass of the object, right? So maybe the apple, for example, right? Taking that universal gravity law, right? And we're just calling this piece here G. And so when we say that the force is m, the mass of the object, so the apple, times g, the acceleration due to gravity at the surface of the Earth, this little constant g is just big G times the mass of the Earth divided by the radius of the Earth squared. And that comes out to be about 9.8 meters per second, okay? Does that make sense? I mean, it's not as profound to us because we grew up knowing that the planets are pulled by the same gravity that pulls things here on Earth, right? So it's not as surprising as it would have been to them back in that time period. But it was a big leap forward, okay?
All right.
I don't know, when you were a kid and you looked up at the moon, did you think, oh, well, it must be falling like an apple falls? Was that obvious to you, or?
No.
No, probably not. You probably didn't think about it much. But, yeah, big revelation, you know, big thought, changed the way that we thought about the world henceforth. What about the product of the masses? Does that make sense, the way that I put it in? I mean, one of the consequences of this, right, let me just show you this real quick. Last thing. So if the gravitational force, right, is big G, M1, M2, let's say M Earth, okay, M apple, divided by radius of the Earth squared, okay?
Yeah.
And Newton's second law says that this is also equal to M apple times G, the acceleration, right, at the surface of the Earth. And we solve for what is the acceleration, right? We get that G is equal to big G M Earth over R Earth squared times M apple over M apple. You see that? We have M apple on both sides, yes?
Yes.
And so when we solve for G, these cancel out. This was a big observation by Galileo, who observed that the rate of change of velocity, right, for objects did not depend on the mass. This was counter to what Aristotle thought, okay? But during Galileo's time, this was a big deal, that feathers and apples really do fall at the same, with the same acceleration, okay? Doesn't matter, boulder or feather, they fall with the same acceleration. This was finally demonstrated. I forget which Apollo mission it was, but one of the moon missions, astronauts actually went up there with, I think, a pipe wrench, maybe, and a feather, dropped them, and you can see they fell and they accelerated, hit the ground exactly the same time. Okay? If you try that experiment on Earth, it doesn't work because you have air and air resistance, and the feather has a lot of air resistance, right? And so it'll flutter down, kind of, right?
Yeah.
But on the moon, there's no air, so you can do that experiment, and it works perfectly, right? Galileo was right that the acceleration of bodies falling do not depend on their mass. Okay? And you can see that's happening right here. This is just one. And now we have G. Little g is what I had pointed out it was earlier. Okay?
Okay.
Does that make sense?
Yeah.
Any questions? Okay. And that's all I have to say about Newton and his apple.